Hello, and welcome to FourthBrain. I am Sohini Roy Chowdhury, the Curriculum Director, and this week I've been working on classification models. I often see that the problems that we find in textbooks are generally too vanilla or too easy, and that's why when we look at real-world problems, we start wondering, well, how can I actually apply the same classifiers or concepts to this gnarly real-world data? At FourthBrain, our mission is to help you work on real-world problems so that you feel more confident once you join your workforce. Let's look at some of the concepts together today. So classification models, let's look at what we got. First of all, we need to understand what classification models are. So by definition, classification models are techniques to categorize objects or samples based off of their shared quality or traits. Now, some of the models that we generally look at or encounter are logistic regression and linear support vector machine, which are linear classification models. And for nonlinear classifiers, we have kernels, SVMs, neural networks, k-nearest neighbors, and decision trees, among a few. And as you can see in the picture right here, classification, typically the job is that if you have these red samples and you want to separate them from the blue samples, you want to figure out the best decision boundary so that you can then say that for any new sample, you can clearly figure out what region or what part of this decision boundary they lie in order to say, well, they belong to the red class or they belong to the blue class respectively. Now, where does the problem essentially originate? The problem essentially originates is most of the classifiers that we study in textbooks, they show the performance on well-balanced data. What that means is, let's say for this particular example, you have 5 pluses and 5 minuses. So this is a 50-50% classification data samples, and then ideally you would fit a nonlinear classifier on a sample space such as this. However, things go a little differently on real world data, especially when you have imbalanced data. What that means is, let's say in this example, it's an 80-20 split. That means you only have 2 samples of blue and you have 8 samples of the pluses. So in this case, estimating a decision boundary can be really hard because of 2 things. First of all, major classifiers always prefer the major class. What that means is if you end up training your classifier such as an SVM on a data like this, it will always have a tendency to prefer the larger class for a test sample. So ideally, think about it, if you are monitoring the number of people who are visiting your website versus the number of people who are actually going through a checkout process. Now, of course, the number of people who are coming to the site is going to be way larger than the number of people who are actually going through the checkout. And that would be a perfect example of real data where the percentage of people who are checking out is much smaller. It's about 10 to 20% corresponding to all of the people who are visiting your site. So that would be a good example of a real world problem. And here, if you have a classifier that has a tendency of always predicting the larger class, well, it is going to be of very little use to you, because typically it's always going to say, yes, this customer on your site is just looking through, but it's not going to really make the purchase, in which case you might actually suffer from low inventory, because if your classifier is not able to give you a heads up that this many number of commodities are going to get sold, then, well, you are going to end up losing customers because you're not able to stack inventory accordingly. So this would be a very real example that you might have to work on in your day-to-day industry job. Now, what could be some of the methods to ensure that you have success in your classification? One good method is called boosting. Let's look at the same data that you have so far, and we're looking at boosting using decision trees. So in decision trees, the first thing you do is first you create a one partition, and that would be this red line partition that you have, which is separating this blue sample from all of the remaining plus samples. Now in this case, you end up in a misclassification, which is this sample right here. So what this ends up doing is you boost the voice of this particular misclassified sample significantly, so that next time the classifier takes into account this boosted sample's voice. So a very easy example for this particular class of models is add a boost. So again, in this case, you end up with another misclassification, you boost that misclassification again, and you form your decision tree. So this would be the final decision trees that you get at the end of boosting. Another method of dealing with such imbalanced data is called SMOTE, or synthetic minority oversampling technique. And again, as the word says, it's an oversampling technique. So what the sample class that you have less number of samples belonging to it, you actually oversample it. So you find the mean and the variance of the distribution and you tend to oversample it. So this would be the oversampled version of the minority class. And the step after that, it's pretty simple, is in order to fit a nonlinear classifier through it. So these would be some of the easy steps that you follow in order to deal with classification on real world problems. Stay tuned for next week.